Our next speaker, Executive Vice President Ahmad Abdelrazaq from Samsung Corporation. Mr. Abdelrazaq is the Executive Vice President of Samsung Corporation, is the head of a high-rise building division in the company, and involved in structural design and construction planning of high-rise and complex building projects, including Burj Khalifa. Mr. Abdelrazaq is now serving as the chairman of American Society of Civil Engineering Committee, and has won numerous awards. Today, his presentation will be on paradigm shift in tall building typologies with the considerations to design and construction technology, in short, new generation of tall buildings. Please welcome Mr. Abdelrazaq.
Thank you. Thank you very much for having me here. It's a great privilege to be joining this conference as a keynote speaker. And also I would like to thank Adrian Smith for taking me under his wing for a long time. Many of the buildings that you have seen, I had the pleasure to work with him very closely on them, anywhere from Seoul to Shanghai to Middle East and so on and so forth. Today, I think obviously he focused Mr. Smith on the architectural aspects of the design, and today I'm going to talk a little bit about the technical aspects of how we bring these very special structure together in integrating the design and construction planning into a single one. And the next one is, where are we going from here? What are the challenges we face as engineers? Obviously, skyscrapers have the power to capture the human imagination because of their scale, their symbolic nature, and to show the financial well-being and the technological advances and the potential for producing very iconic building all around the world. Obviously, we remember cities by their skyscraper, from Chicago to Hong Kong to New York to Singapore to Shanghai, and now we have Seoul. Obviously, many buildings are emerging, and it's time due. Dubai, for me, was a special place for many reasons. Dubai, in fact, gave the architect a free hand of what to do in architecture. So what you can see, all kind of building typologies has emerged that influence what we do today. It seems like there was so much money, there is no end to what we can do there. From the flames, to the rounded building, to the sky gardens, to the dancing towers, to obviously today we are seeing new typologies of tall buildings. And all of these things are bringing a huge amount of challenges to us as engineers and from technological standpoint in many aspects. If we look at the tallest building in 2020 and look at the proportion of these typologies, we can see start building very, very slender. For example, look at this building. It's an aspect ratio very large, or Chicago Spire, where we started to see emerging new challenges from a structural design perspective and new difficulties that we are facing structurally. Obviously, tall building has been all about technologies. Starting from the beginning of the 19th century, where they emerged after the Industrial Revolution, we saw the first buildings in steel, the first buildings in concrete, and then after that, the challenge and the race for tall building system had started, especially in New York, that emerged into the Empire State Building, Chrysler Building, and obviously the Rockefeller Center. After World War II, obviously we've seen the modern architecture and new technologies in terms of the steel. But where we are facing today is, our challenge is dealing with computers. And that all started by the Guggenheim Museum in Bilbao. So what we do today are very much influenced by computer technologies. As you can see, these buildings are iconic, unique, sustainable, but we have to think, what are the key factors that influence the design of skyscrapers, and how can we make them very cost effective, because somebody has to build them efficiently. So today, we'll talk about what are the factors influencing the design of skyscrapers, sustainability as an optimum structural design. The structural system optimization was not recognized by LEED as one of the items, but it's a really key component from the embodied energy that we can have. And if we can manage a gravity system very well, we can maximize the resistance to lateral load with very little penalty to resist these very large forces that we deal with. And also, most importantly, is how do we integrate the construction method into the design principle from the early design concept. The next is, what is the new generation of tall building system would look like? Are we using all of these technologies that we have today in this building design? Obviously, by the Council of Tall Building and Urban Habitat, a tall building that's more than 300 meters is considered super tall. Some of the characteristics of these buildings, technically they need very high technologically advanced because of their height, such as high-rise design with a special consultant, structural stability, faster construction cycle, special equipment, and verticality control, especially for unusual type of building that tend to have a major impact on the serviceability aspects of these buildings. But most importantly is the management aspect. These projects take a long time to build, and communication with the consultants is extremely important. Obviously, they require massive amount of resources and management that all has to be done in one set. The factor that influence design of tall building, again, from my perspective, including financial, they have to be able to generate a profit. Environmental, to improve the living conditions in dense city by creating large open plaza, free more land, provide more natural lights, reduce transportation needs, save energy, long life expectancy. Obviously, all of these is a formula for a dense and concentrated tall cities with tall buildings. But today, well, some of the things that drive the architectural design concept, and we have to think about, is it really free-form architecture? Or is it a creating with sculpture? Or is it the sustainability aspect? Or is it the building codes requirement and restrictions? Engineering design concept and some of the latest technologies, structural design concept, wind engineering, solar energy, latest material and construction technologies. How are we designing tall buildings? Obviously, some of the things that influence the cost of tall buildings, because ultimately you can try to design the tall buildings, and if it's not economical, it will never be built. Shape and geometry are important. Size of the floor plate and regularity is important. Structural solution is very extremely important for many aspects. Facade specification, vertical transportation, environmental strategy, site constraint, and the market conditions, and how we do them. Obviously, many of you have seen this slide and probably got tired of looking at it, but one thing we need to remember, denser cities tend to be more sustainable. And as you can see, going from Hong Kong to Singapore to Monaco. And this is a study that was done by Mr. Marshall Strabela, looking at if we take all the areas in the Burj Dubai and spread it out, what does it mean? We can no longer spread city horizontally. We have to concentrate. We have to create a building within the fabric of the existing city and go up and stop to go horizontally. One of the things that we don't focus on a lot is the embodied energy. What in tall building? Tall building require a huge amount of material, and the material that is needed the most is related to the structure. Everything else, as you can see here, between the structure and everything else remain constant. But as we build taller, building get to use more structural material. So the question comes is, how do we optimize the structure? Obviously, gravity load management is extremely important. That has to be fundamentally embedded into the architectural design concept. I work with it very well. Wind engineering management and treatment, seismic engineering, and looking at the performance-based design, and also vibration control of tall building, and also integrating it with the construction method. And now, today, we have structural health monitoring to give us more than we ever dreamed about because of computer technologies and utilization of advanced material as sustainable energy. Generally, most of you know, probably in order to design building efficiently, we need this much material. And for wind or seismic or lateral forces, depending on the building size and the structural system, could result in a huge amount of material. For me, has always been the challenge, how do I bring this line to that line? And that by itself, it's a good balance and a good structural concept. We pioneered a lot of structural engineering chart by Abdelrazaq Khan. It's about most economical design. Developed systems such as the bundle tube system, which is rarely used. And lateral load resisting system, for example, in the Gemma Tower that I work at SOM with Mark Sarkeesian and Bill Baker and Stan. Again, looking at the integration of these systems, and Adrian, again, you can see the integration of the structure and architecture, and it results in extremely efficient building with a minimal amount of material. Burj Dubai is the same story. How we manage the gravity load system and design. For example, if you look at the total material that is needed for gravity alone to support the structure is that. And because of minimum sizes, this is the total material we used in the building. Essentially almost minimal. No penalty for lateral loads. We talk about bracing, diagonalized bracing. People hated it for a while, and now they're coming to it again because of requirement. Again, it has a lot of challenges in terms of design. And we've done a lot of things in this building. This is one of the research students I did at IIT. It's about 250-story building, which is about half a mile high. Again, if you look at the design of it, it's extremely efficient, and it uses a mega frame system in a very elegant way. When engineering management is extremely important, we talked a lot about that. Obviously, it requires optimizing building dynamics, disorganized vortex shedding, surface treatment, and as you can see from the evolution that Mr. Adrian Smith talked about, this building in particular, Tower Palace 3, when we tested it in the wind tunnel, it did not show any vortex shedding whatsoever. The building was so quiet, and it was the ingredient in developing what we did in Burj Dubai. Again, we talked about aerodynamic shapings a lot, varying the building width, building setbacks, plans, private chamfers, bleeds, and so on and so forth. And this is one of the, another almost 160 story that I did with an IIT student at IIT. This is another one, adding bleeds. Again, from research, looking at Daewoo Tower while at SOM, again, changing the shape is very important and could result, when engineering integration into the architecture, could actually result in a very interesting systems. And today, we're looking at the twisted and tapering building. They are all excellent shapes to deal with the wind engineering aspects. Again, without spending much time, Adrian talked a lot about the concept, what influenced Burj Dubai design, essentially what we did in Burj Khalifa. And if you look at superimposing the shape of Tower Palace 3 is over here, and Burj Khalifa is over there. Again, we did a huge amount of input into developing the shape that goes back to even at chimneys, in terms of, if you look at the shape and how the spiral up of the shape is extremely important. And if you look at the frequency of the building is away from every other vortex shedding frequency that's critical. So the technique for Burj Dubai is used anywhere from the bottom all the way to the top of the pinnacle. And that's how we're able to control the wind forces. Computational fluid dynamics. Now, it gives us a huge amount of leeway in terms of planning this building. Of course, they cannot substitute a wind tunnel, but again, it gives us a lot of ingredients of what we can do related to that. The last formula that we don't use often as engineers now, and I'd like to encourage a lot, is damped structures. Obviously, there are three things that control vibration of a building, in particular the acceleration. One is the stiffness, generalized mass, which is a function of the shape of the building, and the damping. Both the stiffness and the mass require an added material. And today, if we can utilize the damping, which is becoming very economical and very cheap, I think it's important to consider it, to have more confidence in terms of what we do with these buildings. Historically, it was used to solve problems. But today, obviously, there are a lot of issues that are coming up, such as distributed tuned liquid dampers. That's the Lob by Arab, same thing here. Obviously, from a paper that I've seen in the Council on Tall Building and Urban Habitat by Mr. David Lee and Martin Eng, again, you can see the benefit of the reduction of both the forces and also the acceleration on the building related to vortex shedding in the very tall and slender tower. We have used damp system, viscoelastic damper, viscous dampers, to control relative shortening, but at the same time, such as you can see in 7 South, that was done by Bill Baker, again, and in adding damping devices at the end. Tune mass dampers, it's used to control the wind, not a huge benefit from seismic standpoint. But today, where we should be facing is performance-based design. If you look around the world, there's a huge amount of damage that's resulted by seismic engineering. We are, as an engineer, developing buildings that are not sustainable. The damage is not acceptable. I think we need to change the way we do buildings, make them performance, make them stand to the test of time, and including a performance damping system, it becomes very important. Again, it has a huge benefit. If we do a conventional building, this is how much material we typically need. If we start incorporating some of these elements into damping, pace isolation, other dissipation system, we will come up with a cheaper and more economical design that is sustainable. And that's, for me, the damage, containing the damage in building is more sustainable than any other things that we talked about. If you look at Haiti or looking at Japan, if you look at all the disaster that has happened, how do you recover that? We need to think about that as we design buildings. Technology is here, inverted pendulum damper, viscous dampers. Again, initially it has very little use. Now we have a huge amount of use on tall buildings with all kind of different formulas. So as we do structure, initially it was very simple process. Now it's becoming very complicated, and we have the technology to do it well, and the formulas, and the guidelines. So there is no reason not to incorporate it as a part of this building system. This is a building that is done in Mexico by WSP. Again, it incorporated the viscous damping as part of fundamental building system to control the seismicity of the region. Today, we have started looking at even super tall building using mega braces and looking at damping devices that can control the motion and control the behavior of the building with a very little penalty. Mega frame. In fact, when I'm looking at this building without these dampers, it doesn't look as interesting. Adding these dampers, it does add a lot of interest into the building, and it makes it a little bit more interesting. This is one of the projects. I get the privilege, again, to work with Adrian Smith by inviting us to work as a contractor and in a pre-construction service in this project. Again, I get a chance to put my 2 cents worth of idea in terms of what we can do and how we build these buildings. Again, for engineers, always wondering what is the best solution. Is it steel? Is it concrete? Is it composite? Is it with damping system? Again, today we have all kind of materials to deal with. Structural material, high performance, high steel, high post-tensioning, fire resistant, casting, computer technologies. We have whatever we wanted to have, smart systems and materials that can change its characteristics in response to the building needs, space isolation. Again, architects always interesting. How can I make the building light, more efficient? So we need to respond to all of that as an engineer. When engineering consideration, seismic engineering, extreme events, robustness and redundancy. So the engineers, when they're taking a pencil and trying to design a building, they have to think of all these ideas at the same time as we are thinking to work with the architect to develop the whole solution. Again, we can design a lot. We have to have the construction input to find out which is the most economical solution we can develop. Somebody has to look at the cost in a real pace, not just hypothetical basis. And we're seeing a drift in terms of the use of high-rise buildings from office historically to residential, shifted from steel into high-strength concrete. Concrete with its ultra strength, for its strength, modulus of elasticity, mass, damping, moldability, cost effectiveness, continuity, and all of the things that we can do. Essentially, concrete has become a very strong competitor with the steel. Today, we can produce concrete as strong as steel at the turn of the 19th century, 20th century, sorry. More than that, we can know what the building are doing, compare our design to what we are measuring. So in Burj Khalifa, I took it on myself, and Samsung has contributed significantly in incorporating a monitoring system for this building to look at the gravity system, shortening, climate, measurement of the lateral displacement, measuring the overall behavior of the building. We installed a significant number of strain gauges to look at the distribution of strengths and strains, and we kept all of these records online, where we are automatically comparing what we measured versus what we got. And surprisingly, the comparison was excellent. Again, structural building survey, online, real time, that was extremely important. How do you control the verticality of these very super tall buildings? So we went the distance in having a real-time survey monitoring program developed to have at any instant of time where the building is and what kind of correction we have to make almost instantaneously. We measured the foundation, we measured the strains, we calibrated the building, we ran the analysis. Again, the building did drift, and we had to control it. And we, according to our analysis, it was within 5 millimeter difference from what we measured. So it was an exciting thing for us to correlate the theoretical, predicted, to the actual. And we can do it as engineers. Obviously, in order to accomplish that, we developed in-house at Samsung a very detailed construction sequence analysis program that pretty much gave us everything we need to know, from column shortening to lateral displacement. And today, we have installed a very health lateral monitoring program in Burj Dubai to measure the building response almost instantaneously. We can tell what the building is doing every 10th of a second. Obviously, we get the output, and we're getting the input. And essentially, we are constantly looking at the performance of the building under earthquakes and on real time. We look at the spectral to look if there's any chance of a change of the behavioral characteristics of the building, and we look at every 1/10 of a second what the building is doing. And again, there are many other issues to integrate: sustainability, cladding, MEB, electrical, vertical transportation, stack effect, and the list goes on. Obviously, I don't have much time to go through these, and every one of them, such as the cladding, design, function, constructability, are important. Cladding, wind tunnel testing, MEP design and sustainability, electrical design and the vertical transportation system in particular, stack effects, how do you control it and how do you make sure it is very comfortable to the people, fire protection, refuge, escape, and fire. But most importantly, what I wanted to do all of that. The great is we can do all these designs, but in fact, the building is more alive during construction than in actual permanent condition, as you will see shortly. And if, with these super tall buildings, if we do not design them and integrate the construction with it, definitely we will fail with time and cost and the time that it takes to build these buildings. So, having a partner from the very beginning in design as a partner become very important. People who have the knowledge inside logistic, planning, equipment, major conditions that you need to consider in high-rise or complex building structure, 3 ACS, column preceding, 3-day, all the construction technique that you could think under the sun to incorporate it to make the building faster. 3-day cycle, measure equipment, high strength, spire. Again, logistic and the planning is extremely important. Tower cranes, as I mentioned, lift cars, how do you size them, how do you plan them? And one of the challenges that we have to pay for, is there something we can do with the vertical transportation people to do something very special during design to avoid doing these things? Why do we have to pay this extra? Labor, transportation management. We have about 13,000 people working on Burj Dubai. And KJ came every time he wanted to wake up to say, how do I manage these people to get them up and down to do their work efficiently and effectively? But most importantly, pumps, up methods, you know, and you know, complexities. How do you overcome these using column preceding methods, and also again column preceding methods similar to that, and how do we speed from 4-day to 3-day to 2-day cycle, which is continue to be really our target. The whole idea is to reduce the construction cycle of these buildings. For example, the first time we use up method is in Tower Palace 3, where Samsung, I was still with SOM, and they asked, okay, can we skip the outrigger? Sure, no problem. We designed for it, incorporated, no stopping. They saved the 3 to 4 months in construction schedule of this building. Burj Dubai, same. Up method, where you leave the things that lagging behind and we go further with it. We have extreme technologies in a very high lifting, such as this project that you see here in the top cloud in downtown Seoul, Petronas Tower. And also look at the pinnacle lifting in Burj Dubai. But one of the things that always we care about a lot is fire and risk management during construction. As you can see, 13,000 people will be working at the same time. So we have to develop, even during construction, risk factor for these, egress for planning, temporary prevention, safety net, and safety facilities. Again, as you can see, there is a huge number of people that we have to deal with. Are these more than what we have in a permanent building that have to move up and down in the building all at the same time? Of course. So obviously one of the challenge, again, to engineers, how can we integrate these into the original design? Do we have to pay for it? Okay, again, the list goes on and on, but because of time limitation, obviously I cannot dwell on that too much. But essentially what we have today is safe place, clean space that we did in Burj Dubai with a very little loss of life or injuries. And the site team and Mr. KJ Kim and his team need to be congratulated for the safety record of this project. Clean technology is also very important. We care about that. I'll speed up. But one of the things that I wanted to mention about, we are designing big cities. And now what we have is what is called the solar chimney. The question is, when we're designing these very large and new cities, why not incorporate them into the design concept of these things? One of the things that come to my mind is this solar chimney concept and how it generates energy. A huge amount, both the solar and the wind. And one of the things that strike me is Inshan Tower, for example, is a very large development. And if you look, the architects started developing that kind of concept already, right? And the question is, how do we integrate it fundamentally into the design concept? Again, these are my hypothetical project. Again, dealing with the different leaves, the wind, and incorporating some sort of a chimney in the middle is a very, very inviting proposal. The question is, when we do very large planning, how can we incorporate that? Again, we looked at the concept and what it may be, right? The future trend of tall buildings is becoming mega city and mega structure for more sustainable that works within the fabric, existing fabric of the project. So the design trend now today is iconic, unique, and sustainable. But for me, good architecture does matter. Design should be responsible, sustainable, functional, and it should be contextual. And in order to do these very large projects, you need experience, design coordination, technical support, and human resources that can support all of that. And seamless engineering and construction services is important. Reliable engineering, enhanced constructability, responsible construction method for mass construction, method and volume of the work, and also minimize the project budget is extremely important because that's what really the client looking for, material cost, labor, indirect. So these projects require huge and timely decisions, design coordination, early procurement, buildability, time management, cost plan, value engineering, global sourcing, and material specification. How can it be done by designers alone? It can't. It has to engage contractors. And because if we wait too long, like most owners do, and issue the drawing for cost, you'll lose a huge opportunity in cost saving because it's too late. And with that, I'd like to end my presentation. And I thank you for your attention. Thank you.
Thank you.